Assalamu alaikum wa rahmatullahi wa barakatuh. This is Ms. Linda. Today, inshallah, we're going to solve one question on thin film. And you had this question on the final exam this year. Now, before we solve the question, just recap a little bit. What do I mean by thin film? You see the different color that we see when we have oil that's leaking from a car and resting on top of a bottle of water or concrete driveway. These different colors is because of this is example of thin film. So what actually before we also saw the question, if you remember the interference, if you have two rods, one is thick and the other one is thin, and I send impulse in the thick rope, what will happen at the boundary between these two ropes? Here. You see part of the pulse will move in the same direction. It's not reflected, just maybe the amplitude is a little bit less, but I will have no phase change. On the other hand, so both of them, they will be in phase. So when we go from high dense to low dense medium, nothing happened. Both of them, they will be in phase. I will not have any reflected wave in the other direction, upside down, I mean. Now, if I send a wave, if I send an impulse from low dense medium, like thin rope, to high dense medium, like thick rope, here at the boundary, one of them will be reflected upside down, so it will be inverted. You see, this one transfers the same, but the reflected wave will be upside down. So here we'll have out of phase by degree. Now for thin film, I have two cases. First case, if I have here, I have three different layers. The first one is 1.2, so the index of refraction is lower than the second one is 1.3, and to lower again. So remember, when we go to low, thick or higher medium or higher index of refraction, we will have phase difference by pi or lambda over 2. So we have two reflection. The first one here at the boundary, this is the first reflection, and this is the second reflection. So one at the lower surface here and one at the upper surface of the thin film. Now, the second ray, this one, it will travel an extra distance, which equals to double the distance or twice the thickness of the film. So it will go here, and then it will bounce off, reflect inside the thin film, so it will travel double the distance. Now 2nt. Now the first one, the first ray, it will reflect at the upper surface. Since it goes to higher index of refraction, so it will reflect out of phase by lambda over 2. Second ray, it reflects at lower surface, at lower index of refraction. Lower index of refraction will have no phase difference. So lambda over 2 plus no phase difference, lambda over 2. So both of them, they're out of phase. So if I need, so we'll have here one phase shift. So if I want both these two rays, when they meet, I want them to meet constructively. I want to see color, different specific kind of color. So the formula we're going to need, going to use this formula, 2nt will equal m plus half times lambda. Add integer multiple of wavelength, because already we have phase difference, which is lambda over 2. And I need constructive interference. Remember, constructive interference, it should be integer lambda, like n times lambda. It should be lambda, 2 lambda, 2 lambda, 3 lambda, etc. So lambda over 2 plus lambda over 2. If I use this formula, we will have lambda, integer number of lambda. So this formula, if I have one phase shift, I'm going to use this formula. If I need them destructively, and I have one phase shift, so it will be 2nt equals m times lambda. T is the thickness of the film. Okay, now if I don't have any phase shift or two phase shift, like here, like these two cases, here I have, this is the first, the top I have two reflection, one here and the other one here. This is the first one and this is the second one. So the first one, it goes to higher index of refraction. So I will have one phase shift lambda over 2. Now the second one, again, higher index of refraction. So again, lambda over 2. So we'll have two phase shift. Lambda over 2 and lambda over 2 is lambda. So they're already in phase. I need them, these two rays, when they meet, I need them to meet destructively. Okay, destructive, remember, destructive, they should be what? Odd integer of lambda, which means lambda over 2, 3 lambda over 2, etc. So which equation I need to use? If I add lambda plus half or add integer multiple of half lambda, I will have destructive interference. So this is the formula we're going to use if I need them, if I need these two waves to interfere destructively. So let's go back now to our question. Here we have the lens of an optical system is coated with a thin film of magnesium fluoride. So here we have this lens. On the top of the lens, we put material. This material is magnesium fluoride. So this is my film. This is my thin film. We have monochromatic light. The monochromatic light, wavelength of this light. So this is lambda, 656 nanometer. In air is incident on the lens, the angle of incidence theta, the two rays X and Y are shown. So here I have, this is the first, we have two rays. This is the first reflection and this is the second reflection. The first reflection, it will reflect off a high index. Now remember, when it reflects off a high index, we will have phase shift equals to lambda over 2. Now, second one, again, it will reflect of what? Of a high index of refraction. Here, the index of refraction here in for magnesium fluoride, 1.38, and this one is 1.58. So it's still higher than magnesium fluoride. So again, we will have another shift. So here we have two phase shift, lambda over 2 and lambda over 2. It's lambda here for an observer here that's seeing the two waves. Okay, so so they're already in phase. I need them now. I need to have constructive interference. So for constructive interference, the equation 2n, T or D, here he called it D, so I'm going to call it D, equals m times lambda. And for destructive interference, interference. This is twice the thickness of the film. So 2nd, this is d, the thickness of the film, will equal m plus half times lambda. This is the formula because here I have two-phase shift. Okay. So predict whether the ray reflected ray X undergoes a phase change. Okay, we just explained that. Okay, so the two waves are out of phase. We will have a phase shift, lambda over 2, and lambda over 2 is lambda. So to give the conditions for the two waves to come together, we can use this formula for constructive and this formula for destructive interference. B, the thickness of magnesium fluoride is D for the case of normal incident theta equals 0. State in terms of the path difference between the reflected X and Y. It will be 2ND. 2ND. Okay. C, calculate the smallest value of D that will result for destructive interference. So remember the formula for destructive, QND will equal M plus half times lambda. I take N equal 0. So we will have 2ND equal lambda over 2. I need D, so I'm going to divide both sides by 2n. So D will equal lambda 2 times 2n, lambda over 4n. Lambda is 656 nanometer divided by 4 times the index of refraction of the thin film is 1.38. And this will equal 119 nano. Okay, that's it. I think, no, we still have the advantage of the arrangement. I will leave this for you. You can search it. E. Light from a point source is incident on the pupil of the eye of an observer. The diameter of the pupil is 2.8 millimeter. Draw on axis the variation of the diffraction angle of the intensity. So this is one single slit. So one single slit, it will be here, one central maximum, and here we'll have other small maximum. And then estimate in radian the smallest separation of the two distinct point source of light of wavelength that can be resolved. So theta D to a well-resolved theta A should be greater than theta D. Now, what is theta D? Theta D is the angular diffraction of the first minimum. So the equation equal greater or equal. Theta A is S over D. S is distance between two sources, and D here, if I have here the observer that observing the two source of light, and should be greater than D since I have it's circle, so we're going to use the equation for circular aperture, which is 1.22 times lambda over 3. So theta D will equal 1.22 lambda is 656 times 10 to the power negative 9 nanometer, divided by the diameter of this circular aperture is how much? Yes, the eye pupil is 2.8 millimeter. 2.8 millimeter times 10 to the power negative 18. And you should get 2.9 times 10 to the power negative 9 radian.